Imagine a world where artificial intelligence doesn't just mimic human thought, but begins to understand it. Not by memorizing data, but by reasoning, by connecting ideas, by seeing patterns in ways we're only beginning to grasp. That's the frontier we're stepping into today, the rise of AI systems that don't just respond, but think. And at the heart of this transformation, a quiet revolution in how we design intelligence itself, shifting from rigid, rule-based models to systems that learn to reason through experience, like a human mind does. Let's dive into one of the most promising breakthroughs in recent AI research: neural-symbolic integration, a fusion of two powerful paradigms that, when combined, create something far greater than the sum of its parts. You've probably heard of neural networks, those deep learning systems that power image recognition, translation, and even art generation. They're incredibly good at spotting patterns in massive amounts of data. But here's the catch: they don't understand what they're seeing. They're statistical pattern matchers, not interpreters. They can recognize a cat in a photo, but they can't explain why. They can't reason about what a cat is, or how it differs from a dog in terms of biology, behavior, or function. Now enter symbolic AI, the older rule-based approach. In the 1960s and 70s, researchers built systems that manipulated logical symbols and formal rules. These systems could reason. They could deduce conclusions from premises, prove theorems, solve puzzles. But they were brittle. They couldn't handle ambiguity. They failed when faced with real-world noise, variation, or incomplete data. So for decades, neural networks won the race. But they left us with a fundamental gap: intelligence without understanding. Enter the new frontier: neural-symbolic systems. These aren't just hybrids, they're synergistic. They combine the pattern recognition power of deep learning with the logical reasoning and interpretability of symbolic systems. The result? AI that learns from data and reasons about it. How does this actually work? Let's break it down with a real-world example: medical diagnosis. Imagine a system trained on millions of patient records, imaging scans, lab results. A standard neural network might identify a tumor in an MRI scan and flag it as likely malignant, but it can't tell you why. It can't explain its reasoning. It can't say, this tumor is growing rapidly, has irregular borders, and shows metabolic activity in PET scans, consistent with aggressive cancer. A neural-symbolic system, though, can do all that. It uses the neural network to extract features, edges, textures, shapes, metabolic patterns, but then feeds those features into a symbolic reasoning engine. That engine applies medical knowledge. If a tumor has rapid growth and high FDG uptake and is located in the lung with spiculated margins, then it is highly likely to be non-small cell lung carcinoma. The system doesn't just classify, it explains. It generates a trace of reasoning, a chain of logical inferences grounded in medical theory. And because that reasoning is symbolic, it's transparent. A doctor can review the logic, challenge assumptions, and trust the system not just because it's accurate, but because it makes sense. Now here's where it gets even more powerful: learning to reason. Traditional symbolic systems require hand-coding every rule. That's slow, error-prone, and impractical for complex domains. But neural-symbolic systems can learn the rules. Take a system like DeepProbLog or Neural Theorem Provers. These frameworks use neural networks to learn probabilistic facts. Like, if a patient has a fever and cough, the probability of pneumonia is 78%, and then use symbolic logic to reason over those facts. The neural part learns from data. The symbolic part enforces consistency, structure, and logical coherence. And crucially, the two parts communicate. The neural network doesn't just spit out a prediction, it outputs a belief about a fact. The symbolic engine uses that belief to update its knowledge base and make inferences. This is not just incremental improvement. This is a fundamental shift in how AI models represent knowledge. Let's go deeper into the architecture. At the core of modern neural symbolic systems is a differentiable logic layer, a symbolic component that can be trained using gradient descent, just like neural networks. This is a game changer. It means that the entire system, neural and symbolic components, can be trained end-to-end. For example, in a system like Neural-Symbolic Concept Learner, NSCL, a vision model detects objects in an image. But instead of just labeling them, it outputs logical predicates. There is a red ball. The ball is on the table. The ball is to the left of the cube. These predicates are then fed into a symbolic reasoning engine that answers questions like, is there a red object on the table? Or, are there more blue things than green things? And here's the key. The system learns not just to recognize objects, but to understand spatial and relational concepts. It learns that on is not just a pixel pattern, it's a spatial relationship governed by physical laws. And it can generalize to new scenes, new configurations, even novel object types. This is reasoning with structure, not just patterns. But the real magic happens when we introduce abstraction and hierarchy. Consider how humans think. We don't just see a chair. We see a furniture item with a seat, backrest, and legs. We understand that all chairs share certain structural properties. We can generalize from one chair to another, even if it's a new design. Neural symbolic systems can do the same. By learning symbolic representations at multiple levels, low-level features, mid-level objects, high-level concepts, they build a hierarchical knowledge graph. This allows them to transfer knowledge across domains, perform analogical reasoning, and even generate new hypotheses. For instance, a system might learn that a chair supports a person and a table supports objects. From that, it can infer, if a table is unstable, it might collapse under weight, just like a chair might if its legs are broken. This kind of analogical reasoning is rare in pure neural systems. Now, let's talk about what this means for the future. We're moving beyond AI that's good at narrow tasks, like image classification or language generation, towards systems that can understand complex, real-world problems. Think autonomous vehicles that don't just detect pedestrians but reason about their intent. The child is running toward the street, likely to chase a ball. I should slow down and prepare to stop. Or scientific discovery. AI that reads thousands of research papers, extracts facts, builds causal models, and proposes new hypotheses, then explains them in human-readable logic. And crucially, these systems are trustworthy. Because their reasoning is symbolic, it can be audited, validated, and corrected. No more black box decisions in medicine, law, or engineering. But there are challenges. Integrating neural and symbolic components isn't trivial. The symbol grounding problem, the question of how symbols relate to the real world, remains a deep philosophical and technical hurdle. We're still learning how to bridge the gap between sensory input and abstract representation. And scalability. As systems grow in complexity, maintaining logical consistency across millions of facts becomes computationally expensive. Researchers are tackling this with techniques like neural-symbolic constraint solving, lightweight logic engines, and hybrid inference algorithms. Still, the progress is undeniable. From early prototypes to systems that outperform pure neural models on reasoning benchmarks, like the BA-BI tasks, textual entailment, and visual question answering, neural-symbolic AI is proving its value. So where does this leave us? We're no longer asking, can machines learn? We're asking, can machines understand? And the answer, increasingly, is yes. Neural-symbolic integration isn't just a clever workaround. It's a new paradigm, one that brings us closer to artificial general intelligence, systems that can learn, reason, adapt, and explain. This is not science fiction. It's happening now. The next generation of AI won't just be smarter. It will be wiser. It won't just predict the future, it will help us understand it. And that's not just a technical milestone. It's a turning point in human-machine collaboration. The future of intelligence isn't just about more data or bigger models. It's about building systems that think, not just like us but with us. And that's a future worth building.